Okay. This is where I want to pick up. Do you guys remember yesterday when we got to this point right here, the 1.5 over 0.99, and people popped it in their calculator? Yes. We said we got 1.51 repeating. I want you to look up here at this series that they described. What happens if I add these two? $1.515, right? And then it has this plus 0.00015. What do I get if I add those two together? 1.51515, right? And it has this dot, dot, dot after it, so this process kind of keeps going, right? What do you notice about this and what we said it was in decimal form? What did we say?
Still repeating, because that's repeating in the end.
Yes. So this is starting to repeat itself, correct? And we see that it keeps going on. We're going to take this process and kind of reverse it. If I give you something that is a repeating decimal, like this right here, can we take it and write it as a rational number? So here's the first example of this process. We are going to express 5.427272727272722 as a rational number. What do I mean by rational number?
Number that ends.
It's a number that ends, but specifically it's a number that I can write as a fraction. A number that I can write as a fraction of whole numbers. So some whole number divided by some other whole number. That's what we're going to do here. First, I need to identify the part of this that is not repeating. Is there any part of this that does not repeat? 5.4. This is our non-repeating part. It's going to get treated differently. So I have 5.4 plus, the part that repeats is what?
0.227.
Yeah. So if I were to write this out similar to what we just saw in that last example, this would be 0.027 plus 0.00027 plus, and then I could keep going with this. So far, so good? Okay. We're going to deal with the part that I wrote in blue, the non-repeating part, later. Right now, I just want to focus on the repeating part. The repeating part represents a geometric series. There is a pattern here where the next term in this sum is the result of multiplying the previous amount by some constant ratio. How would I go about finding what that constant ratio is? Divide what?
The one with 3 zeros by the one with 1 zero.
The one with 3 zeros by the one with 1 zero. 0.00027 over 0.027. Y'all are going to love me for this. We need to know how to do this without a calculator. I will let you use calculators on this test. But on the final exam, there are certain questions where they do not allow you to use calculators and certain questions where you have to. This is not hard to do without a calculator. This is not hard to do without a calculator. Sort of. I need to move my decimal point first. How far do I need to move it on the top so that I'm dealing with a whole number? 1, 2, 3, 4, 5 places, right? Okay. So I would have a 27 up in my numerator. If I move it 5 places on the top, I need to move it 5 places on the bottom, correct? 1, 2, 3, 4, 5. So my decimal point moves here. What do I fill in those missing gaps with? Zeros. So I have 2,700 here. Can we reduce that to what? 1 over 100, which is the same as 0.01. You guys want to know a trick on the repeating decimals? If you have 2 decimals that are repeating, or sorry, 2 digits that are repeating, in this case it's 27, 27, 27, 27. If 2 digits are repeating, our R value is 1 over 100. What do you think it would be if I have 3 repeating decimals? 1 over 1,000. What about if it was just 1 repeating decimal? 1 over 10. Is that R value smaller than 1?
Pretty much.
So if the absolute value of R is less than 1, what can I do with this? Yes, I can find the infinite sum. Does this meet that criteria? Yes, it does. I can find the infinite sum here, so we're going to do that. The infinite sum is equal to the first term divided by 1 minus r. If I'm looking at just the geometric part, because remember I told you we're ignoring this non-repeating part for now. When I'm looking at just the geometric series part, what's the first term there? 0.027. Over 1 minus r, what did we say r was? 0.01. What is 1 minus 0.01? 0.99. So I have 0.027 over 0.99. I really don't want a fraction with decimals in it. How can I deal with just whole numbers here? What did we do there? Yep, we're going to multiply. We're going to move our decimal point over. How many places do I need to move it in the numerator? 3 places. 1, 2, 3. So that numerator becomes just 27 over, if I move it 3 places up top, 990. Can I reduce that at all?
Yeah.
What goes into both of those? 3. Anything bigger? 9 can go into both of them. What would I get if I reduce this by 9? 3 over 110. So that is how the repeating part gets represented as a rational. Now we're going to start dealing with this non-repeating part. I have 5.4 plus 3 over 110. Because 3 over 110 is this repeating part right here. What do I need if I'm going to add these two things together? I need a common denominator. This is something else that you need to practice doing without a calculator. Multiply 5.4 by 110. So that would give me, what, 440 and 5500.
So 5940. What have I not written down yet? Not quite. Decimal place. Where should I put the decimal? Behind the 0? I got to put it right here because we had 1 decimal place right here. So I have to move it over 1 place here. So 594 would be my numerator. Over 110. Plus 3 over 110. That shouldn't be too bad to add together. What is that? 597 over 110. Grab your calculators real quick. I want to verify that that really is 5.4272727272772. Did you get that original repeating number? Good. All right. Let's try one more example like this, and that ends 10.3 for us then. You guys ready? Okay. Take a couple minutes, try the process on your own, and then we'll do it together. I'm going to give you guys about 3 or 4 minutes to work on this on your own. And then we'll come back together and go through it a step at a time.
how would I begin representing this as if it were a summation? So what's the non-repeating part here? 2 plus 0.146 plus what? And then it would just keep up with that pattern, right? So we have part of this that is geometric. That's this part right here. That is a geometric series. And then that 2 in the front is the non-repeating part. So we'll deal with that at the very end. What is our R value here? 0.001. So I'm going to write it out similar to what we had before, moving that decimal place 1, 2, 3, 4, 5, 6 places. So 1, 2, 3, 4, 5, 6 places. I need 3 zeros back here. 1, 4, 6, 0, 0, 0. So 1 over 1,000, 0.001. And I'll move that into the space where you can actually see it. There we go. Can I find the infinite sum? Yes. So the infinite sum would be equal to what? 0.146 over 1 minus 0.001. What is 1 minus 0.001? 0.999. So 0.146 over 0.999. How would I write that as a rational? Whole number over whole number. 146 over 999. Trying to keep my stuff from running into itself. Okay, so now I worry about that 2 part because I've represented the geometric part as a rational. So I'm going to do 2 plus 146 over 999. What do I need so that I can actually add those together? What do I need to have so that I can actually add those 2 together? I need a common denominator. How do I write 2 with a denominator of 999? $1,998. So I rewrite this as 1998 over 999 plus 146 over 999. What is 1998 plus 146? 2144 over 999. Does that reduce? You said yes? What does it reduce to?
Oh, never mind. No,
In decimal form, is it what we started with?
yeah.
Yes. Yes, it is. Do you guys have any questions about how to do this part of it now? Process is pretty much the same. However many decimal places we have that are repeating, that's how many zeros we're going to get in our denominator for our R value. And then we take it from there. So far, so good? That finishes up 10.3. So we are going to start into 10.4 next. 10.3 homework is due tonight. There is no 10.4 homework. I gave you guys the test review so you can start focusing on that once the 10.3 homework is done.
I decided not to do 10-4 homework so that you can just prepare for the test as far as homework goes. 10.4 is dealing with mathematical induction. Mathematical induction. Do you guys remember doing proofs in geometry? So, I asked about that because that was probably the first and only time that you guys have had to prove that something is true, correct? Mathematical induction is a way of proving certain things are true. It's not the same as our geometry proofs. No two columns, no webs, no nothing like that. Mathematical induction is specifically used when we're working with sequences and series. You know how we have those formulas to be able to quickly sum up an arithmetic series? We wrote the formulas down to be able to add up an arithmetic series, and we have one for geometric as well. There are lots of other types of series out there, and they have their own shortcut formulas. So what we're going to be looking at is how to use the process of mathematical induction to prove certain things true. The big idea behind mathematical induction, with each positive integer n, so that's what we use as far as like first in the sequence, second in the sequence, third in the sequence. If the associated statement P sub n is true, so some function rule associated with this sequence, then all statements Pn are true, provided that this is true for the first term, that's the P sub 1, and that if I make the assumption that this is true for the term that falls kth in line, the kth term, however far over k happens to be, if that one is true, and I can show that the one after that, the term k plus 1, if that is also true, then it's true for every single term in the sequence. Steps to using mathematical induction. There are two parts to mathematical induction that go along with these two principles. In order to do a proof by mathematical induction, the first thing we have to do is show that this is true for the first term. Whatever it is that we're trying to prove, we have to show that it's true for the first term. Once we've shown that it's true for the first term, we're going to assume that it's true for the one that falls k in line, and I'm going to use that assumption to show that it has to be true for the one that comes right after that. That's what I mean by P sub k plus 1. We are going to do one example today, and we'll do a couple more on Monday, and then that'll end chapter 10 for us. You guys ready to look at an example? I'll write down these steps as we do the example, these two steps here. All right. Our first example problem. We're going to use mathematical induction to prove that for every positive integer n, the sum of the first n positive integers is n times n plus 1 divided by 2. So here is what that statement is saying. going to actually move that off to the side here. But this is what we are going to prove. So step one, show that this is true. For P sub 1.
So positive integers beginning with n, in this case n is 1.
So what I need to do is show that 1 is equal to, anywhere I see an n, I'm going to replace it with a 1. 1 times 1 plus 1 over 2. What is 1 plus 1?
2.
2. So I have 1 times 2 over 2. And 2 over 2 reduces down to what? 1. So is this true for the first term? Yes. Step 1 is done. Step 2. We will assume that P sub k is true. And show that this means P sub k plus 1 is also true. So I'm going to write down what our assumption is then. We will assume that 1 plus 2 plus 3 plus everything up until we get to k is equal to k times k plus 1 over 2.
This is the sum of the first n positive integers, and I'm ending with k because we're talking about P sub k. So far, so good? That is equal to, instead of n, I'm replacing it with a k here. So k times k plus 1 over 2. We're just beginning with, suppose for a minute that that's true. If I can use that fact to prove that P sub k plus 1 is true, then it is true for all values.
So we need to show that 1 plus 2 plus 3 plus all the way up to k, and then one term after k, that would be k plus 1, is equal to what I have up here in red. Anywhere we have a k in red, I'm going to replace it with k plus 1. So this k right here, I'm going to replace that with k plus 1. This k right here, I'm also going to replace with k plus 1. Over 2.
We doing okay so far? A little bit. I'm taking k plus 1, and I'm putting it in these spots for n here. Okay. Let's focus just on the left-hand side for a minute. The left-hand side, where I have things written as a sum. I'm going to recopy that right here. I want to focus on just this part of it right here. So I'm looking at the sum of 1 plus 2 plus 3 plus all the stuff up to term k. I'm going to leave that one out for right now. We made an assumption about all of this, didn't we? What did we assume about all of this? That it is equal to k times k plus 1 over 2. So I'm going to engage in some substitution here. I am going to substitute in our assumption. So I'm going to replace this with k times k plus 1 over 2. And I'm going to bring down the plus k plus 1. I have a rational expression right here, something that has been written as a fraction. And I want to add that to something else. What do I need to add something that's been written as a fraction to something else? I need a common denominator. So I have k times k plus 1 over 2 plus 2 times k plus 1 over 2. Now I've got that common denominator. So I can add those two numerators together. I'm going to have to drop down a line here in a minute. How many terms are in my numerator? How many things separated by pluses or minuses? 2. I have 2 terms in my numerator. What do you notice both of those terms have? K plus 1. If I have 2 terms and they have a factor in common, what can I do with that?
Take them out to the front.
I can take it out to the front. I can factor it out to the front. So I'm going to factor out a k plus 1. What would I have left over if I factor that k plus 1 out? K plus 2. And we still have it all over 2. Let me draw an arrow so we can actually follow along here. Can I rewrite k plus 2 as being k plus 1 plus 1? All right, so let's do that. So I'm going to rewrite this as k plus 1 plus 1. Why do you think I just did that? Yep. This right here is exactly the same as what I said I wanted to show. This is the same as this. I just proved it. We just proved it. We used this assumption right here to show that the next one would also have to be true. And so our proof is complete.
If you are sufficiently confused yet, welcome to mathematical induction. It gets better with practice, but the first couple times you look at it, you're like, what? It's a super powerful proof technique, though. Any future math classes that you take where you have to do proofs, this one is very, very powerful because we're talking about things that go on for infinity. How do you prove that something is true forever? It's not like we can go test every single case. So this is a way for us to show, as long as I can show that the first one is true, and I show that somewhere down the line, if I pick a random term, and I assume that that one is true, and then I can show that the one after it would have to be true, then every one after the first one would also have to be true. We'll do a couple more examples on Monday. I don't want to bog you guys down too much, but I want you to get a little bit of practice with this and a little bit of exposure under your belt. You have the review in your hands. There is no homework over 10.4, so you can focus on the 10.3 homework tonight, get that finished up, and then you can turn your attention to the review. On Tuesday, you guys will have time to work on the review in class. Wednesday, we will go over whatever you'd like. I'll see if I have time to put together Jeopardy or something, and then we'll have your test on Thursday.